Okay, welcome back. And today we're going to start the last section of chapter 1, which is on the least squares um, line. And so we're going to talk about how to calculate this, what it is, first of all, and then why is it important, and what is it used for. Okay, so let's look at a data set here. So this is accidental death rates in the United States. And this is from year 1920 to 2010, and the death rate represents the number of accidental deaths per 100,000 in the population. Okay, so notice that as time has gone on, that the accidental death rate per 100,000 has been going down. Okay, and so one of the things we want to do is we want to plot this on a what we call scatter plot. And a scatter plot is where we have two axes, one for different variables, right? So this would be our x variable. Time is always independent, so this would be our x variable, and this would be our y variable. And we're going to plot this on a on a plot, and we're going to call that a scatter plot. And the reason why we do that is to see if there is a linear relationship between the two variables, right? Is there a relationship, and is that relationship linear? Okay, so if we do that, then we get something like this, right? So here's the year, and here's the death rate. And so we get this scatter plot, and you can see that there is a downward trend, as we also saw in the numbers. It is going down, okay? And so now what we want to do is, if we see that there looks like to be a linear relationship, okay, we want to find, well, what is the best line? Because I could draw all kinds of lines through this. You know, if I want to draw a line, I could draw a line here. Oops. Right? I could draw a line through here. I could draw a line this way. I could draw a line this way. I mean, my line, my artistic skill notwithstanding. But you get the point, right? So the question is well, what's the best line? And that's where the least squares line comes in. Okay, and that's what we're going to talk about. So before we discuss what is the least squares line, what we're going to do is let's take this example of this line here. Notice that this line here goes through the middle of the points, but it doesn't go through all of the points. Okay, and notice that the distance from this point to the line, right? This is how far the line was off, right? This is how far off we were. If we were to use this line as an estimate, we would get this value if we used this equation of this line, but we would be off, right? There'd be an error, right? So the distance here would represent the error that we made, okay? So notice that this distance is below, but then this distance is above because this dot is above the line, okay? And notice that the distances for each dot is different, right? Some are small, some are large, right? And notice that we have these 10 points, so we have 10 distances. And so we have these 10 distances, and this would be distance 1 or d sub 1. This would be d sub 2. Okay, and the reason why we say d sub 3 is because 3 is a subscript. So instead of saying d3, we could say d sub 3, or d with a subscript 3, but instead of saying all that, we can just say d sub 3. Okay, so we've got all these distances. Well, here's where the least squared line come in. What we want to do is we want to find the line, we want to plot a line that makes the overall distances the smallest. So in other words, we want to minimize the overall distances. Okay, we want the overall distances to be as small as possible. Okay, but knowing that as we move the line closer to this point, it's going to move further away from other points. So we want to figure out where do we need to do the line so that the overall distances is minimized. Okay, so now also notice something. Because some of these distances are below the line, they're going to have a negative value, and the distances above the line are going to have a positive value. Well, if we start adding negative values and positive values, they're going to sort of cancel each other out. And if the line is right smack dab, like we're going through the middle, we're going to end up with a value that's very close to 0. Okay, which is going to be problematic. It's not going to be helpful, as you'll see. So this is where we're going to end up squaring the distances. Okay, because we want everything to be positive. So what we're going to do is we're going to take all the distances that we see here, and we're going to square them. And then what we're going to do is our new goal is going to be, okay, let's take all these squared distances and let's sum them up and find the line that makes the sum of all of these squared distances the smallest. And that line is going to be the least square line. Okay, and that's how it's derived. Okay, so now to get the least squares line, here are the two formulas. Because we're talking about a straight line, we're going to use the mx plus b, right? So y equals mx plus b, and this is going to give the best fit line through the data points. And so these are all the data points that has a slope of m and a y-intercept of b. And these are the formulas for the slope and for the y-intercept. Okay, notice that for the y-intercept, it includes the slope. Okay, so in other words, another way of looking at this is y bar, because we're divided by n. This could be also written as b is equal to y bar, the average of the y's, minus m times the average of the x's. But since we're not going to get into that right now, but this is the formula for the intercept. This is the formula that we would have to use for the slope. They're complicated looking formulas, okay? So we're going to talk about this, but then we're going to show how to get this in the calculator. So on your calculator, there's a couple ways of doing this. So you could use the formulas, obviously. Okay, so all you have to do is use to take the products of x, y. So you take all the x, y values and you take the product of them and you sum them up. Okay, and then you take the sum of the x's, the sum of the y's, and so that's or the sum of the x squares. Those are the numbers that we're going to need to put in here. Okay, so you could use the formula. Now, instead of using the formula, you could use a table, because these are all of the things we're going to need. Because so for every year, right, so from 1920 to 2010, so for all of the years, so these are the years, so x represents the years from 2000, and y represents the accidental death rate per 100,000. Okay, so now here's our x and y. So then what we're going to do is we're going to take the product of x and y. So we're going to multiply across, and then that's what's going to give us all of these numbers. And then to get this column of numbers, we're just going to take this column and square them. So this gives us all these numbers. Okay, and then to get y squared is we're just going to take this column and square all these numbers, and that's what gives us these numbers. Then if we sum down all of these columns, that's going to give us the numbers that we need to put into the formula. So here's our sum of x, here's our sum of y's, here's our sum of x times y, our sum of x squared, and our sum of y squared. We can also do it in the calculator. Okay, so instead of using a table like this in our calculator, we could do it in our calculator and let our calculator do the work. So because all we have to do in our calculator is go to Stat Edit on your calculator, and then enter in your X data, your years, and then enter in your Y data, and then guess what? To get this column here, let's say, all you would have to do is put your cursor up on L3 at the top, and then what happens is your cursor, all you have to do is type in what you want in this list. So in this case, if I want to have the products of my X and Y, then I would put in L1. So I would put in L1 times L2. So just to see this, so you would type in L1 times L2. Now the way you get L1 and L2 is you would do second and then the number. So you would hit the second key, okay, on your calculator, and then you would go to the number key that you want. So if you wanted L1, you would do second 1. If you wanted the L2, you would do second 2 on your calculator. Okay. Then once you do that, hit enter, and it will automatically take the product of L1 and L2 and stick them in here. And then if you wanted x squared, you would do the same thing in L4. You would highlight L4, and then you would put in L1 down here. You would put in L1 squared, and then hit enter. And you could do that all the way across. And then what you could do is you can sum the columns to give you your numbers. Okay. So again, ask me about this in class, and we will do examples of this, and we will get practice using the calculator. No problem at all. Okay. But there's another way we can do this that's even better, and that's to use your calculator function, linreg. So one of the functions in your calculator that is very powerful is your linreg, because when we find the least square line, another way of looking at this is called a linear regression. A linear regression line uses the least squares regression line, or the least square line, which is what we're talking about. So if you use linreg, linreg will automatically give you the formula for y equals mx plus b. Now it'll use a and b, but it'll give you your two numbers. It'll give you the slope and it'll give you the intercept, and all you have to do is write out the equation. And there's also a way to store this in your calculator as a function, so you can graph it over here on your calculator. But again, let me know, ask me questions, because we'll do examples of this in class. So again, this is one thing you're going to want to practice. So here's another example of accidental death rates. So notice that this is the line. Okay, so again, this is a typical graph. Okay, so you've got year, and you've got death rates, and then you can plot this. By the way, you can plot this on your calculator, and in fact, I have a video. If we don't do it in class, I'm going to have a video to show you how to do the graph in class, but we'll definitely be doing this in class, and we're going to be getting practice doing it. Okay, now, what about, okay, so let's go back. So now that we've got this, now we've kind of put the cart in front of the horse, because we normally don't do regression until we look at this, what we call the correlation. Okay, but there's two things going on here. We've got the best fit line, the least squares line, but also we want to know, hey, how strongly correlated are the two variables? Is there a strong correlation, a moderate correlation, or a weak correlation? Well, that's where the correlation coefficient comes in. Now, the correlation coefficient is this monster of an equation. Okay, the correlation coefficient uses all of these summary statistics again, these calculations that we did before: x times y, sum of x, sum of y. By the way, just so you know, these are sigma notation. This is a Greek letter sigma, and this Greek letter sigma means that I'm summing all of the values in here. So this means I'm taking all of the products of x, y, and then summing them. This means I'm taking all the x values and I'm summing them. This here, I'm taking all the y values and I'm summing them. That's all that means. Okay, so it's a summation notation. And so then we got these values down here. So if we take this calculation, we can calculate the correlation coefficient R. The correlation coefficient R tells us how strong is the linear relationship, keyword linear, relationship between variable x and variable y. The closer this value is to positive 1 or to negative 1, the stronger the correlation. The closer to 0, the weaker the correlation. So if we look at these graphs, so this is the first thing we normally look at. We look at the graph and we say, okay, is there a linear relationship? So if there is, so this here has a perfect linear relationship, and it's positive because look at the slope. The slope is positive. So R is going to be close to positive 1. In fact, if we get something like this, it'll be it'll be pretty much exactly 1. Look at this one. This is again a very linear relationship, and it's going to but it's a negative slope, so the correlation coefficient is going to be close to -1. Here, these two are nonlinear relationships. So because R only measures linear relationship, both of these are going to be very, very, very close to 0. Okay? So now notice that when you use linreg, again, you have to put your diagnostics on. Okay? So make sure you go to your catalog on your calculator. Okay, which is the 0 key. It's the under catalog. So it's above the 0 key. If you go to your catalog key, then you're going to go down to your D's, right? And you're going to look for diagnostics. Okay, you're going to look for diagnostics. And you're going to look for diagnostics on. Okay, then you're going to hit enter. And then once you hit diagnostics on, once you hit enter, you'll see diagnostics on your home screen. Hit enter again, you're going to get done, and your diagnostics are on, and they will stay on. Why do you need your diagnostics on? Because if you don't have your diagnostics on, you will not see these two values. This is the one that we're interested in. That's our R value. So our R value is the correlation coefficient. And that's what's going to tell us how strongly correlated or how strong the association is between the two variables. Okay? So now if we look at this scatter plot, look at this scatter plot. Okay, so first of all, notice that we get this cluster. Now, again, this is where subjectivity comes in. You might look at this scatter plot and say, oh, there's nothing, there's no linear relationship here. It's just like a cloud of dots. But there also, somebody may look at it and say, you know what? Even though it looks like they're far apart, there is a trend. It does look like there's a linear trend. You know, maybe it's moderate. Maybe there's a moderate correlation. Maybe there's a weak correlation. You know, we really don't know until we look at the correlation coefficient. Hold on. So that's one thing. Okay, so we can look at the correlation coefficient, and we can find out if there is based on the correlation coefficient, maybe there might be a weak, moderate, or strong correlation. And it does look like there might be a positive correlation too. Okay, but the other thing to look at is notice this here. Okay, now, so this is the state 8th grade reading score. Okay, so, and this is the average expenditure that they spend by state. So how much money per student do they spend on average? And so we see that there seems to be a positive linear correlation between how much money the state spends on their kids per student on average, and their reading scores, how well they read. Okay. Now, notice this here. Now, this dot here represents Washington, D.C. Now, notice how far this dot is from the rest of the pack. This dot is so far away from the pack that we might consider this what we call an outlier. Because if we include this point in the data set, it will bring down the correlation coefficient to really small. In fact, in this data set, it will bring it down to like 1, or excuse me, like 0.1, okay, which is pretty small. Now, if you don't include this point, it jumps up to 0.4, which you might consider maybe a moderate or maybe a moderate correlation, okay? But the point is, this one point severely affects the correlation coefficient. And so when we look at the scatter plot, we might want to take a closer look at points like this, because if they are indeed outliers, we do not want to include them in our calculation. Okay, now, if there is, now just because they're an outlier doesn't mean that we just get rid of them automatically. We only get rid of them if they're a mistake. If they are an outlier, but the data is not wrong, I mean, the data is correct, we still want to look at this closer because there may be information here. Why is that? Why is this point so far from the rest of the trend? Okay, there might be something else going on there that would be of interest. Okay, but again, the main point is this might be an outlier. Okay. Okay, and that ends this section. So again, bring your questions to class. Write your questions down. Start doing the homework. Start doing the examples in the textbook. There are other examples. Start working on some of the exercises at the end of the chapter for practice. Okay, if you get stuck on something, bring those questions, those problems to class, because those are the problems we want to work on in class so that we can get this under our belt so we can get understanding so you guys can do well on the quizzes and the exams. So again, take care, and I'll see you in class. Have a great day.